So let's start talking about polygons by naming some polygons. If we know the number of sides or the number of vertices that a polygon has, we can give it a name based on that number. And we've already talked about a couple of different types of polygons and named them. For example, a three-sided polygon is a triangle, and a four-sided polygon is a quadrilateral. And we even went so far as to talk about special kinds of triangles or quadrilaterals. So we could have an isosceles triangle, or we could have a rhombus. So we gave some special names to these two special polygons. But now we're going to give some names to some polygons that have even more sides. A five-sided polygon is a pentagon. A six-sided polygon is a hexagon. With 7 sides, we have a heptagon. 8 sides, we have an octagon. 9 sides, we have a nonagon. And 10 sides, we have a decagon. Now, if we go beyond 10 sides, we have names that we can give those figures, but we're going to generalize this to say that any polygon that has more than 10 sides, so we'll just use n as a placeholder here for more than 10 sides, we'll call an n-gon. So a polygon with 17 sides we would call a 17-gon. A polygon with 23 sides we would call a 23-gon. So take a look at this polygon. Think about how many sides it has, or you could count the vertices. It has 6 sides and 6 vertices, so it's a hexagon. And it also has some angles that are contained within it. So suppose we want to find the sum of the measures of all of those interior angles. Now obviously those interior angles are different sizes, so without any additional information we can't find the measures of the individual angles in this particular hexagon, but we can find the sum of all their measures. So here's how we're going to do it. We're going to think about taking these angles and breaking them up into smaller pieces. And the way we'll do that is by drawing some triangles. So from one of the vertices, let's draw some diagonals to create some triangles. So we can make a triangle and another one and another one. So it looks like we've got 4 triangles that the interior of this hexagon has been broken into. Now the reason why that's important is we know something about the sum of the angles in a triangle. We know that each triangle has to have a total interior angle measure of 180 degrees. So if we look at this triangle that we've marked with green angles, we know that all of those green angles have to add up to 180 degrees. And this triangle that we've marked its angles in blue has to have angles that add to 180 degrees. And this one with pink angles, all those pink angles add up to 180 degrees. And all of these orange angles also add up to 180 degrees. So now we've got all of these angles inside the triangles, which if we put them back together would give us all of the interior angles of the hexagon. So we'll put together all of the angle measures that we have. And since we have 4 180s, the sum of all the interior angles would be 720 degrees. Now stop and think about what's going on here. We had a 6-sided polygon. We were able to, from one vertex, divide that polygon into 4 triangles. And so the sum of the interior of the hexagon was 4 times that 180 degrees. Now let's see if we can use that same idea to find the sum of the measures of the interior angles of a decagon. We know that a decagon has 10 sides. So think about how many triangles we could draw if we pick a vertex out and start drawing diagonals from that vertex. So we've got 10 sides, and we can divide it into 8 triangles. Each of those 8 triangles has a total angle measure of 180 degrees, so the sum of the interior angles of the decagon is 8 times 180, or 1,440 degrees. So let's generalize this. What is the sum of the measures of the interior angles of a convex n-gon, where n could be any number of sides? Well, we know that if we have n sides, we can draw diagonals from a vertex, and we will be able to create n minus 2 triangles. Each of those triangles would have an angle sum of 180 degrees, so the sum of the interior angles of an n-gon is n minus 2 times 180 degrees. And that actually gives us a formula we can use to find the sum of the interior angles of any polygon. Now you noticed in that last example that decagon looked kind of lopsided. And that's because the sides and the angles were not all the same. A regular polygon has congruent or equal size sides and congruent angles. So this hexagon is a regular hexagon. It has 6 congruent sides, it has 6 congruent angles. Compare that to this one. It's also a hexagon, but the sides and the angles are not congruent, so it would be an irregular hexagon. So how are you going to know when you have a regular polygon? Well, it's going to be one of two things you notice. Either you will be told outright that it is a regular polygon. So if I tell you on the left we have a regular hexagon, then you know that all the angles are congruent and all the sides are congruent. What if I don't tell you that it's a regular hexagon? How are you going to know that it is? Well, you have to be a little careful with this. If all I tell you is that the sides are all congruent, that's not enough information to know whether or not it is a regular hexagon. That's no guarantee that the angles are congruent. But if I tell you that the angles are also congruent, then I know that I have a regular hexagon. Now, one other thing to keep in mind when we have regular polygons, and that's something we've talked about before, which is this idea of rotational symmetry. So if we have a regular hexagon, it has 6 sides, then it's going to have 6-fold rotational symmetry. So we would be able to rotate this hexagon around its center, and in 6 rotations we would be able to return it to its original position. That's something that's true with any regular polygons. So if we had a regular decagon, it would have 10-fold rotational symmetry. So we've talked about the measures of the interior angles of a polygon, and we've talked about what a regular polygon is. So let's put those two ideas together and try to figure out what the measure of any one single interior angle of a regular decagon is. So here's a regular decagon. It has 10 congruent sides, 10 congruent angles. Remember, if we wanted to find the sum of all those interior angles, we could think of dividing that decagon into 8 interior triangles. Each would have a total angle measure of 180 degrees. So the sum of all the interior angles of this decagon is 1,440 degrees. Now that's not exactly what we're looking for, but it's close. We want the measure of any one single interior angle. And since this is a regular decagon, all of the interior angles are congruent. They all add up to 1,440 degrees, and there's 10 of them, so that means each single interior angle has to measure 144 degrees. So now let's think about what exterior angles of a polygon would be. And we're going to look at this pentagon as our example. We know what the interior angles are. They're the angles inside the polygon. The exterior angles are formed if we take each of the sides of the polygon and extend it out. So if we extend this side out, we can look at this angle as an exterior angle. And if we continue to do that all the way around, we'll find that we have 5 exterior angles on this polygon. If it happens to be a regular polygon, then all 5 of those exterior angles would be congruent. Now what if we wanted to find the sum of the measures of all of those exterior angles? Well, let's think about it this way. Let's say that we were starting at that vertex of this pentagon and we wanted to just walk around the pentagon. So we're going to think about the angles that we would turn through to get back to the beginning. So we'd walk to this vertex and we'd turn that amount, walk to this one and turn that amount, and we would continue to turn and turn and turn, and we'd be back to our original starting point. So the question is, what was the complete amount of rotation that we did? How far did we actually turn to get back to the beginning? So let's look at this one more time. See if you can count how many times we actually rotate around. Okay, so think about it. The arrow started in this position, and then it rotated around and ended in the same position, and it actually only made one rotation. So what's the sum of the exterior angles of the polygon? Well, it would be 360 degrees. And as it turns out, it doesn't matter how many sides a polygon has. The sum of the measures of the exterior angles in any polygon will be 360 degrees for exactly the reason we saw here. If we would walk around the exterior of the polygon, we would make one rotation to get back to the beginning. Now we have one more thing to talk about, and that's something called a polygram. So if we have a polygon, we can create a polygram by drawing some diagonals around that polygon. We have to draw the diagonals consecutively, which means where one diagonal stops, the next one starts, and we have to have some sort of pattern to follow. So let's look at this as an example. Let's say we want to draw a 5-2 polygram. So the 5 in the 5-2 means that we're going to start with a 5-sided polygon. So we're going to start with a pentagon. And the 2 is telling us the pattern to follow when we draw diagonals. So we have to begin by picking a vertex to start at. And it doesn't matter which one you start at, so I'm just going to pick one. We're going to start at that vertex. Then you have to pick a direction to go. And it doesn't matter whether you go clockwise or counterclockwise, as long as you keep going the same direction. So I'm going to go clockwise. Now the 2 is a pattern of counting from the vertex that we started at. So if from that vertex I count clockwise 1, 2, and then I connect my starting vertex to my ending vertex, I will have my first diagonal. Now from where we stopped, we're going to keep on counting to 2. So we'll count 1, 2, and connect the end of the last diagonal to where we stopped counting. And we're just going to continue that all the way around. So we'll count 1, 2, and connect. And then 1, 2, and connect. And then 1, 2, and we're finally back to where we started. So we've got a 5-2 polygram. Now that may look like a familiar shape to you. I mean, you may be thinking of it as a star, You might remember seeing that from the Donald Duck in Math Magic Land video. They called that a pentagram, and it was something that was of importance to the Pythagoreans because they found the golden ratio within that pentagram. So if you go back and look at that video again with that Donald Duck in Math Magic Land, you'll see that golden ratio in this pentagram. Now, another thing to keep in mind with these polygrams is that when you're done, you will always see that you have two diagonals that have been drawn from each vertex. In this case, by the time we got back to where we started, we had two diagonals drawn from each vertex, so we were finished. But as it turns out, there's going to be some cases where that isn't true, and we'll have to continue drawing. So let's look at this. This is a 6-2 polygram we want to draw. We'll start with a 6-sided polygon, so we'll start with a hexagon. We'll pick a vertex to start at. I'm going to start with that one on the left again. We pick a direction to rotate. I'll go clockwise again. And we will count 1, 2 vertices to connect up the endpoints of our diagonal. And then we'll count 1, 2 again, 1, 2 again, and we've ended up back where we started. Now remember, we have to have two diagonals coming from each vertex, and we don't have that. So what we're going to have to do is go to another vertex that does not have two diagonals coming from it, and we're going to have to continue the pattern. So there's 1, 2, 1, 2, 1, 2, and we have our 6-2 polygram drawn. Now, one thing that you need to notice that will give you a hint that you're going to have an additional starting point is if you think about the relationship between 6 and 2, and almost think of it like a fraction. So if we had the fraction 6 halves, we know that there's a common factor of 2 between 6 and 2. So if you think about the fraction 6 halves, that would simplify to the fraction 3/1. So if I ask you to draw a 3-1 polygram, it would actually look like a triangle. So we end up basically drawing two triangles for this polygram. So as usual, we'll get to practice some of this in class.